Yeah, start.
Okay, Assalamualaikum and good afternoon to our beloved lecturers, Dr. Maisara, Dr. Parvina, and Prof. Hailiza. So today we are from Group V. My partner Tan Vivi and I, Nur Arfah, are going to present about solving linear congruence. Okay. We can start by defining linear congruence. A congruence of the form AX congruence to B modulus M, where X is an unknown integer. It is called a linear congruence in one variable. It is important to know that if A if X if XO is a solution for a linear congruence, then all integer xi such as xi congruence XO mod M are solutions of the linear congruence. Okay. Method of solving. Solving linear congruence, AX congruence B mod N. If GCD AN equal to 1, then one solution exists. Since 1 divide B, this 1 can be divided by B. If GCN AN equal to D, then the solution exists if D is divisible by B. Method of solving. Usual or normal method by additional, subtraction, and multiplication of congruences. Properties. Other properties, other method. The first one using extended Euclidean algorithm and divisible algorithm. Second one is using Euler theorem. And the third one is Fermat-Little theorem, which is very similar to Euler theorem on condition that AP minus 1 when P is the prime number. Next. Okay, look at the example 1. X congruence to 2 modular 3. Notice that GCD 1, 3 equal to 1. 1 is divisible by 2. Thus, in particular solution for x equal to 5, then x equal to 5 plus 3t, where t can be 1, 0, 1, 2, and so on. Or x also can be 5, 8, and 11. Example 2. If integer n for the mod involved is big, for example, x is 7 modular 100. In this particular solution, x equal to 107. Then x 107 plus 100t, whereas t can be 0, 1, 2, and so on. For x 7, for x congruent 7 modular 1000, in this particular solution, x equal to 1007. Then x equal to 1007 plus 1000t, whereas t can be 1, 0, 1, 2, and so on. Okay. Moving on to example 3. If integer for involved is big, for example, 1000x modular 1000x congruence to 2 modular 3. The GCD is 1003 equal to 1. A solution exists. Then using extended Euclidean algorithm and divisible algorithm, or since mod 3 we can easily substitute 0, 1 or 2. We can find the particular solution for 1000x congruence to 1 modular 3 is 1. We can check that by multiply 1 by 100 and minus 1 divided by 3. It is equal to 999. Now we can solve 1000x congruence to 2 modular 3 by multiply both sides by 1. We check the value x for 0, 1 and 2, and we can find that 2 multiplied by 1000 minus 2 and then divide by 3, it is equal to 666. So x can be congruence to 2, congruence to 5, congruence to x, and congruence to 11 mod 3, or can return as x equal to 2 plus 3t, t equal to 0, 1, 2, 3, 4, and so on. Okay. Verify extended Euclidean algorithm. 1000x minus 3y equal to 1. 1000 equal to 333 multiplied by 3 plus 1. And then 1000x minus 333 times 3 equal to 1. Then x equal to 1. Okay, this we can refer to this to verify and check which 1000x congruence to 2 modular 3. You can refer the table here lah. Okay. So my partner Tan, he will continue with example 4.
Okay. I will talk about the example 4. This 3x congruent to mod 9. What is the solution? Obviously no solution because it's 3 not divided by 2. We look at the 3an. GCD an, I mean a is 3, n is 9. So GCD is 3. 3 cannot divide. 3 cannot divide 2. Okay. So we got the example 5. This is a multiple solution. 5 solution because GCD is 5. GCD for 535 is 5. GCD an is equal to 5. So how we simplify to the this residual system. So we got x congruent to 2 mod 7. Previously is 5x. We divide by 5, we got 2. So it will be 7 times 5, that means we got this one. We got the b. So ax congruent to b previously is 5x congruent to 10 mod 35. That means we got x congruent to 2, 9, 16, 23, 30 mod 35. Because the least reducer system is time 5 back. So we time 5 back, then got the original for the linear conclusion, linear congruence. So the t is from 0, 1, 2, 3 until 4. So got 5 solution. We go to the next example. Using Euler theorem, because got mod, you can solve it using Euler theorem 7x. A v n congruent to 1 mod n. This is a Euler theorem. How to use it? We divide it to get the inverse. Get time back, get inverse. We got the line a times the a v n minus 1 times b congruent to b mod n. This is the equation for the inverse, red color. And we go to the next slide, will be Euler theorem. This slide. We substitute or plug in the value. We mix up the slide. Now is mod 13. And we plug in the A is 7, and then B is 2, 13. So A is 7 here. The phi 13 is prime, minus 1, go to 12. Phi is 12, that means P Vn is 12. That means we got 12, and then minus 1 again, we got A power 11. A is 7, so A equal to 7 power 11 times 2. We got a value here. I mean, you got this, the value, we simplify the value. So you got something point, the integer, and then got a 0.307. So the count is 4. The remainder is 4. You can check it. 4 over 13 is 0.3076. So its remainder is 4. And then we look at Fermat-Little theorem. A power p minus 1 congruent 1 mod p. We divide the A and then time A back. We got the equation line 3. So the inverse is A power P minus 2 times B. Time B. So this is the inverse. So Fermat-Little theorem, we plug in the value. Okay. A is 7. Here is P. P is prime. Put the prime back in. So the inverse is A power P minus 2 times B. And then times B again. No, it's just time B. B is 2. So inverse is prime is 13. So minus 2 is 11 back. Oh, the slide is, we check down here. You can verify 7x, same as Euler theorem, x congruent to 4 mod 13. You can verify for the 0.3075. So same as congruent, we mod 13. So the end of the presentation, We stop here. Thank you, everyone.